Um, Hopefully this won't be, I've had some audio issues, but hopefully this will be chill. I'll try to get through this efficiently. We're talking about resonance. Um, I know I'm muted, it's okay. Okay, so resonance, this is building a lot on what we've been talking about with Lewis structures. For this class, I'm going to define it, which is a bit inaccurate, but whatever. We're going to call it resonance when we have a molecule where, like what we've seen a lot already, when you have a molecule and there are multiple valid reasons to, valid ways to represent it in a Lewis structure. Like we have multiple valid electron arrangements. Okay, so I'll call it that for this class. Keep it simple. In this class, I will also tell you when I expect you to think about resonance. But I just want to point out, because this is such a big, important topic, if you ever choose to do more advanced chemistry, just want to point out that often we might recognize this when there's symmetry, and very often we're talking about like double bonds moving around, and so to enable that, you'll usually see like double or triple bonds that are next to lone pairs and can kind of switch places with lone pairs. I'll just call it that for today. But those are some patterns you might notice. So let's talk about what this actually implies and why it's so big a topic. So O3, ozone, perhaps something you know about. Let me just draw the structure for you. Hopefully you can figure out some of these. So my three O's. Of course you'd want to go through the actual process of finding these if you were asked to, but looking at this guy, hopefully we can kind of recognize there's nothing actually like fundamentally different about like the left oxygen versus the right oxygen, right? As I was going through this process of making a Lewis structure, I might have chosen to put my lone pair on the right, but you could, or sorry, my double bond on the right, but you could have chosen to put it on the left. It'd be equally as valid. The fact that that exists is called resonance. And just to get a little bit more detailed, for you guys, I feel like when you're doing resonance, you're just going to like try to come up with multiple valid things, and that will kind of work. But I might challenge some of you to maybe make your first Lewis structure and then think about how our electrons might move around, because in reality, that's kind of what we're representing here. So, like, instead of having this lone pair, I could take those electrons and I could make a double bond. My oxygen gets a little overwhelmed. It can't just have 4 bonds, so this bond is going to get kind of kicked off and become a lone pair. And I could find a different resonance form where my double bond is on my left side and my single bond is on my right side. Something like that. So those are called resonance forms of each other, and we're going to want to make sure we have this double-sided arrow to show that. Okay, cool. And again, I won't ask you this on a test, but I want you to have a little bit more understanding of like what the heck is going on and why resonance matters. And that's something, I think we could kind of represent that with something called a hybrid structure. I'm just going to talk about it for a little bit. It's not that like half of the ozone exists where the double bond's on the left and half of it exists where it's on the right. In reality, like these are equally favorable, right? There's no reason why it would be on one side or the other. So what's actually happening is as this exists, it's constantly switching back and forth between these forms. And it's just constantly doing that. So it's not that some of them are one form, some of them are the other. It's actually that those electrons are moving positions constantly. And so it's more accurate to say that they're kind of like in between. So it's not that one's a double and one's a single. It's kind of like they're both like 1.5 bonds. Like those electrons are just moving through the structure, through those two different resonance forms. Okay. So something you might see sometimes when we're talking about resonance, we might see a hybrid structure. So that would look like this for ozone, showing that you have those single bonds. And then we just would kind of do a dotted line to show that sometimes that's a double bond, sometimes the double bond's on the other side, and we might just label it that like that. You might also see it, some people might throw a little negative there, showing that at any given time, one of those oxygens might have more electrons, more electron density, we call it. Again, not something I'd test you on, but something you might see and kind of helps us understand resonance. So, I'd encourage you to try this one on your own, see if you can make a Lewis structure on your own, see if you can come up with other versions of it. But we already did this in class, actually. This guy. And we have a double bond, and we have some electrons scampered around like that. As we talked about in class, we're going to make sure we label it as an ion for our audience. So maybe you come up with that one. It's equally as likely we could make a resonance form with any of those oxygens. So your other resonance forms would look kind of like this. Again, I'm going to show that double-sided arrow to distinguish between my resonance forms, but one of them might look like that. And then another might look like this. But all of those are resonance forms of each other. I could say that my nitrate ion has 3 resonance forms, and I can kind of just looking at this tell they're all equally favorable. There's no difference between those oxygens. Again, I may pause it, see if you can try this one. Can you name it? Or can you figure out what it is? I have just 1 sulfur, I have 3 fluorines. There are lots and lots of forms if I look at this. Again, I encourage you to just use this as an opportunity to practice, see if you can make its Lewis structure. Maybe you'd come up with this one. So, sorry to skip steps, but, take the time to practice, look back at your notes if you aren't super comfortable with how I might have gotten that. This is okay because sulfur has that expanded octet, so there's a bunch of different options. I could go with just one double bond like that, and this will work as well. See if you can come up with more, but we could probably come up with a whole bunch of these. You can do triple bonds, you can do some combination of single and double. There's lots, as long as it's following our 2 rules, same total that you started with, everyone's stable, then it's good. So that's just kind of, why did I make that an oxide? Sorry, I did it right. Try oxide, so 3 sulfurs. Hopefully you caught me before I caught me. Anyway, so that's the basic concept. If you want to try thinking about how your electrons might move around, that might help you figure out your resonance structures. Maybe I'll give them to you if they're a little challenging. Maybe you just start over and make a different choice. Like instead of making a double bond here, try making a double bond here, something like that. But it just kind of takes some practice. I feel like you guys will be pretty good at it. So the nitrate one, obviously symmetrical, right? Like there's no difference between these structures really, besides that I moved that double bond around. But sometimes it does matter. Sometimes, like some of the other examples we've already seen in class, they're not actually equal resonance forms. One is more favorable, one is more stable, or not more stable, I'll say more favorable. They're just happier with that arrangement of electrons. The only difference between resonance forms is different arrangements of electrons. So one might ask, which one is the best one? Which one is the most favorable? And so what you're going to do is check something called formal charge. And I'm going to give you a little formula. And what we're going to have to do is check our formal charge for every single atom in our molecule. And we'll compare structures after doing that, and we can tell which one is best. So there are more complicated versions of this formula. For this class, let's keep it simple. The formal charge of an atom. What I'm going to encourage you to do, just look at what's attached to your atom. So this formula is basically a calculation to show, like, everything needs 8, right? Everything needs stability. But some things can handle electrons more. If I'm more electronegative, maybe I prefer lone pairs. I want to have those electrons to myself. I like electrons. If I'm not as electronegative, I'd probably prefer to have shared electrons. I still want stability, I still want 8, but maybe I'd prefer a bond rather than having those electrons to myself. So kind of a weird concept. You don't need to be able to explain it, but the way I recommend you do it, you're kind of comparing, okay, how many valence electrons do I start with? So like from the periodic table. And I'm going to compare that to what I actually have in my structure. So the easiest way I think for you guys to think of it is just number of the dots attached and the number of lines. So again, comparing what you started with what is actually attached, what is your distribution of electrons in the actual structure. So you'll get a numeric value for each atom, and how do we know if that makes it more stable? To even be resonance structures. Remember, a valid resonance structure, a valid Lewis structure. We've got to follow our rules. We need the het rule. 8 electrons, or exceptions. Okay. And when you do this, they have to add up to 0. Like, you're going to have multiple numbers. They have to cancel out, or, you know, if you have an ion, they have to cancel out to the charge. If these rules are not obeyed, your structure is wrong. Back it up, try again. Something must have gotten mixed up at some point. But this will be true for every single structure you make. But making a preferred Lewis structure. So again, formal charge, that calculation for each atom. Ideally, if something has a formal charge of 0, it is at its ideal electron distribution. That's perfect. If you can have all zeros, that's your best structure. But a lot of the time, they're not all zeros. There's no structure where everyone's a 0. There's going to be a little bit of tension there. Well, that's fine. As long as it's a valid structure, it can exist. If you have to be non-zero, you want a negative charge. So like more electrons in the space. You want that to be on your most electronegative atom. So reminder, that's a really important property we're going to think about a lot. It means attracting electrons. So if I'm good at attracting electrons and being around electrons, I'm happy to have a negative formal charge. I'm happy to have those extra electrons, or that, you know, those unshared electrons next to me. Reminder on that trend, most electronegative means closest to fluorine. Remember, the trend goes up to the top right, stops at fluorine. Okay, so these are the rules that you're going to keep in mind to make your decisions. So these terrible Lewis structures I made on my computer. Let's go through, and again, you're going to do this formula for every atom. So let's look at my oxygen right here. I want to find its formal charge. And our formula for that, starting electrons minus dots and lines it's attached to. So periodic table, it starts with 6 valence electrons. And I'll compare that to the fact that it has 1, 2 dots and 1, 2, 3 lines. So the formal charge on this oxygen is a +1. It's still stable. It has 8 total, but technically the distribution is a little bit low. A little bit, like there's not as many dots as it would prefer, but maybe that's okay. So it's kind of repetitive. Again, formal charge. Starting electrons. Starting valence electrons is 4 for carbon, and it has 1, 2, 3, 4 lines attached to it. So, if possible, carbon likes having 4 bonds. That's what gives it a formal charge of 0. Over here, formal charge is equal to starting valence electrons, 6 for oxygen, minus its 6 dots, and its 1 line. This one has a formal charge of -1. And I like to label them like that, just to keep track of what I'm talking about. Pause and practice. Can you use this formula? What do we plug in here? Comparing my initial valence electrons to what it has in the structure. So again, I'm just using that formula from up there, comparing starting valence electrons to number of dots and lines. Okay, so you go through and you do all that, and then the question is which one is more favorable. And again, we have these rules up here to help us evaluate that. So looking at this one, if possible, again, what a zero formal charge means. Zero formal charge is saying this is the most ideal arrangement of electrons for this atom. So I noticed with this one, that is going to be our most stable because they're all zeros. So you could have some kind of explanation like that. Again, please try the next one, see if you can figure it out. Have this weird little ion I've drawn for you. Formal charge for each one is what you need to go through and do. Maybe I'll do this one for you guys. So again, starting valence, which is 5 for nitrogen, minus the 2 dots and the 3 lines it has. Okay. The 4 starting minus the 0 dots and 4 lines it has. Okay. So for this one, it's going to look like that. And that's allowed. That's okay. I'm going to leave the rest to you. Please, use that formula. Make sure you can get these numbers. These are all our formal charges. Practice doing it on your own. Okay. So then to pick the best structure, we're going to compare our neighbors. We're going to compare our formal charges with the different structures. So hopefully looking at this, there's like an obvious one we're going to rule out. And that's going to be this one. So you can make notes about this if you'd like. I'm going to rule this one out because these numbers are like the biggest of our options. Like these ones are closer to all 0. So this last one's definitely not going to be my favorite. But I have 2 different ones that look pretty similar, right? They both have 2 zeros and 1 negative formal charge. Okay, so I feel like we get tripped up when we see that. But remember, here's our rules. Here's our tiebreaker. If we need non-zero formal charges, it's better for the negative to be on the most electronegative atom. So think back to that. Think about your trend. Is it better for your negative to be on the O, or is it better to be on the N? And hopefully after remembering your trend, you remember that the more electronegative atom, the one closer to fluorine is oxygen. So I'm not going to write this out for you, but please write it out as I say it. This is going to be our best one, because if we have to have that negative formal charge, it's more stable, it's more favorable for it to be on the more electronegative atom. So it's better for that negative to be on the O rather than this N. Okay, so that's kind of the concept. Hopefully not too bad and pretty similar to what we've been working on. The rest of this packet is practice problems. Just like the last honors assignment, these ones are pretty similar to what these examples look like. You should be able to do those pretty straightforwardly. That's the kind of question I might ask you on a quiz. These ones I want you to do eventually before turning in this assignment, but they're not going to actually be in the quiz. So if you need a little bit extra time for the last pages, go for it. They're supposed to be a challenge for you. I'm not going to show you exactly how to do them. I want you to use your noggin a little bit and think about, so you know this concept of resonance, of the double bonds and stuff moving around. There's some stuff about what that might do to your properties of your atoms, or how it might change your bonds. And I think it's cool to challenge you and make you think about that. So that's on you guys to work on when you get the chance. But again, these first 2 practice pages are the more important ones. If you feel comfortable with that, and like the other stuff is a challenge. It's supposed to be a challenge. Don't freak out. And I think that is all I have to say. Hopefully this is helpful. And yeah, bye. And I can't remember how to turn off the recording. Sick. Just watch me do that. Okay, perfect. Goodbye.